All right, this is the review for quiz 2 for trigonometry. And we'll start with some true-false questions that you could see on the quiz. State the domain and range for f of x equals the inverse sine of x. You need to use the interval notation. So in order to get the domain and range for the inverse of the function, you need to first remember the domain and range for the original sine function that we restricted to make sure that it was 1-to-1. So for the original sine of x, the domain, the restriction was from negative pi over 2 to pi over 2. And the range from the typical sine graph, the range goes from negative 1 to 1 on the y. Now you have to recall that for the inverse function, the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. So the domain for the inverse sine would be from negative 1 to 1, and the range would be from negative pi over 2 to pi over 2. Same thing for the cosine function. So the original function, the cosine of x, we restricted the domain to make the function 1-to-1 to go from 0 to pi. And then the range is the same for the original function as the sine of x, which is negative 1-to-1. So then the domain of the inverse would be the range of the original. It's negative 1-to-1, and the range of the inverse would be the domain of the original. Okay. Now, tangent function. So you need to recall that for tangent, it is very similar as sine. The only difference is that the endpoints are not included in the interval. So domain would be from negative pi over 2 to pi over 2 with parentheses instead of brackets. That excludes the endpoints. And then the range would be from negative infinity to infinity on the tangent function. There's no restriction on the range. Now for the inverse tangent, again, the inverse has the domain and range flip-flopped. So the domain of the inverse would be from negative infinity to infinity, and the range of the inverse would be from negative pi over 2 to pi over 2. Okay, vertical asymptotes for f of x equals tangent x on 0 to 360 degrees, so on the whole unit circle. Okay, on this one, you need to, again, recall a couple of trig facts and some algebra facts. So we need to recall that the original tangent function is the same as sine of x over cosine of x. You need to recall from algebra that the vertical asymptotes happen when cosine of x, the denominator, is 0. And then from the unit circle, you need to figure out where the values of x are 0 on the unit circle. And then you will figure out that the vertical asymptotes for the tangent function happen at x equals 90 degrees and x equal 270 degrees. We're in degrees because these values were given in degrees. Okay, vertical asymptotes for cosecant. It's the exact same logic, so let's go ahead and run through it. Cosecant is 1 over sine. Vertical asymptotes happen when the denominator is 0. So sine x would be 0. And then from the unit circle, sine is 0 at 0, pi, and 2 pi. Now, notice there's no equal sign on the 2 pi, so we don't technically need to include 2 pi. The 0 degrees takes care of the 2 pi. We are in radians this time too, so we'll use radian measures. So x equals 0 radians and x equals pi. We don't need to put the word radians after pi. Pi already signifies that it's in radians. Okay, cotangent. Same exact logic. Cotangent x equals cosine x over sine x. So again, the vertical asymptotes happen when the denominator, or sine x, equals 0. Since it is the exact same as the one before it, it will be the exact same vertical asymptotes here. X equals 0 radians and x equals pi radians. Again, 2 pi is not included. There's no equal sign next to 2 pi. And secant. Secant x equals 1 over cosine x. So the vertical asymptotes happen when the denominator, so cosine x, equals 0, and cosine is 0 at pi over 2 and 3 pi over 2. This time we're in radians and not degrees, unlike part D with a tangent. So we need to make sure and stay that way. So vertical asymptotes, x equals pi over 2, and x equals 3 pi over 2. You also need to know the shape of the graph of all 6 trig functions. You will be matching them to graphs. So all of them, sine, cosine, tangent, cotangent, secant, cosecant, you need to be able to recognize them and match them to their original function. The periods and the phase shift, it's very similar to what we did on exam 1 with sine and cosine. It's just now tangent and cosecant on here, but you can see cotangent and secant also. It really all is very, very similar. So let's go ahead and run through these. The first one is tangent. We'll start with a vertical stretch. Stretch factor. And that is the absolute value of the first number. So this is 2. The period for the tangent function. So unlike sine, cosine, secant, and cosecant, the fundamental period for tangent and cotangent is not 2 pi, it's pi. So it is pi over b, which in turn was pi over 4. B is 4 in this case. And then phase shift. Phase shift is c over b. My c is 32. My b is 4. 32 divided by 4 is 8. This is a positive phase shift, so it's 8 to the right. But if you just leave it as positive, I am going to assume that positive means to the right. Okay, same thing for cosecant. We have stretch factor. That's the absolute value of the first number, and it's just 3. We have the period. So this time the fundamental period is 2 pi, so this is 2 pi over b, which is 2 pi over 1/2. B is 1/2. So 2 pi times 2 over 1, 4 pi. Phase shift. Still c over b. C is negative pi over 4 this time. B is 1/2. So negative pi over 4 times 2 over 1. Reduce the 4 and the 2. You'll get negative pi over 2. Negative phase shift means that you're going to the left. You can write it as pi over 2 and write in the word left. I will take that too. For the following exercises, evaluate the expressions exactly, use radians in your answer. So this is just a unit circle exercise, and you need to ask yourself, What is it that you're finding? Here, because it's all inverse functions, you're finding the angle of the value that gives you the sign of whatever is inside that parenthesis. So for the first one, I'm not going to write it for every one of them, but for the first one, you will be finding, so find angle theta such that sine of theta equals 1/2. And remember, there is a restriction on this. And theta is in the interval from -π/2 to π/2. Okay, well, sine of theta is 1/2 for π/6. Π/6 is in that interval, so the answer is just π/6 here. I will go down to part B, inverse cosine of -1/2. It's a little bit different for cosine, that's different interval. So we need to find angle theta such that cosine of theta equals -1/2, and theta is in the interval from 0 to pi this time. Well, cosine is negative in the second quadrant, and the second quadrant is inside this interval, so the answer is just 2π/3. You can look it up on the unit circle. Okay, now inverse sine of 3. This is going to be undefined, and that is because 3 is not inside the domain of the function. So the domain of the inverse sine is from -1 to 1. Since 3 is not in the interval from -1 to 1, and we can't really force it to be in that interval, that value is undefined. All right, we'll go ahead and run through the cosine. Inverse cosine of -3, square root of 3/2. This is you're looking for theta such that cosine theta is negative square root of 3/2, and theta is in the interval from 0 to pi. Once again, this is in the second quadrant, and this is 5π/6. A little more logic for tangent, for inverse tangent. So inverse tangents of -1. So this time you're looking for theta such that tangent theta is -1. And theta is in the interval from 0. Ooh, nope, that's not right. From π/2, -π/2, to π/2. Okay, notice the parentheses instead of a bracket. The endpoints are not included here. Just think logically a little bit. For tangent to be -1, sine and cosine have to be the same value. Only one of them needs to be positive and one of them needs to be negative. Since this interval, the -π/2 to π/2, that's quadrant 4 and quadrant 1. We cannot go into quadrant 2. So what needs to happen here is that sine will be negative. We're in quadrant 4. Sine will be negative and cosine will be positive. Tangent theta is sine theta over cosine theta. In quadrant 4, sine theta is negative square root of 2/2. Cosine theta is square root of 2/2, which is -1. But it is true for theta equals -π/4. We cannot give the angle from quadrant 4. We have to go in the negative direction in order to not violate this restriction on the inverse tangent. All right, arctangent, which is the same as inverse tangent, arctangent of 0. So think about it. Tangent theta equals 0. Now, tangent theta is the same as sine theta over cosine theta. For tangent to be 0, cosine cannot be 0. That would be undefined. So sine has to be equal 0. For this fraction to be 0, sine theta has to be 0. Now, sine is 0 at 0 on the unit circle, at 0 or pi. But pi, it's the same interval. Pi is not in this interval, so we cannot use pi. This has to be just 0. Okay, a little bit of a word problem here. Find the angle theta in degrees in the given right triangle, round answers to the nearest hundredths. So on this one, we have a hypotenuse given, and we have the side that's opposite to the given angle. When we're given an opposite side, that is a sine problem. So sine of theta equals opposite over the hypotenuse, which means that theta is inverse sine of 7/10. Put it into a calculator and you should get 44.43 degrees. This problem did say answer in degrees, so make sure that your calculator is set on degrees before you start doing calculations. On number 5, we have a bunch of composition of trig functions. So we will go ahead and run through this. On these, I will ask you to explain why you got your answer. So you actually do have to write down the explanations or step-by-step solution in order to get full credit. I know you can put these into a calculator, which is why I'm going to ask for explanations. So on the first one, inverse cosine of 5 pi over 6. When you have the function and its inverse, which is what it is here, so inverse cosine of cosine, you need to make sure that you are checking the insides. So this angle right here, if that angle is in our allowed interval, then the answer is just that angle. So let's go ahead and check that. 5 pi over 6. It is in, the restriction for cosine is this interval, 0 to pi. And 5 pi over 6 is inside that interval. Since the angle value is inside the interval, the answer is just that angle value. Okay, part B, we have sine on the outside, inverse sine on the inside, so still work inside out. On this one, 2 is not inside the interval from -1 to 1, the domain of the inside function. So the answer is just undefined. We cannot make it be inside that interval. So undefined. D and E is probably acceptable. D and E does not exist. That's a shorter way to write it. All right, let's do part C. We have, okay, this time we have a combination of two different functions. Unlike A and B, where it was a function and its inverse, part C and D have a combination of two completely different functions. So not the same rules. Inverse sine of cosine of pi. On these, you're working inside out. So first of all, you're going to calculate cosine of pi. So this next step is really not negotiable. You have to have it showing. Otherwise, I will take off some points because you're not showing enough work. So cosine of pi, this value right here, that is -1. So that's what's going inside this parenthesis. And then you're doing inverse sine of -1. So find theta such that sine of theta is -1 and theta is between -pi/2 and pi/2, which will be -pi/2. Okay, and then the most cumbersome one, inverse tangent of 12/5 inside and then cosine on the outside. Again, start with the inside function. So you have to remember that this is an angle of some sort. I'm going to call it theta. So really what we're trying to find is cosine of the angle theta. Now this angle theta has a tangent of theta equal 12/5. Tangent is only defined from -pi/2 to pi/2 to be 1-to-1. So this has to be in quadrant 1. I'm going to go ahead and draw a little triangle in quadrant 1. This is your angle theta. Tangent is opposite over the adjacent. We need to find the hypotenuse, so we won't be able to get the cosine value. So let's go ahead. H squared equals 12 squared plus 5 squared. H squared is 144 plus 25. H squared is 169. H is the square root of 169, which is 13. Now, we just need to find the cosine of that same angle theta. So cosine of theta is adjacent, which is 5, over the hypotenuse, which is 13. Okay, ladder question. Suppose you have an 18-foot ladder to reach a second-story window in the house. If the window is 12 feet off the ground, what is the angle in degrees that the ladder is making with the side of the house? Okay, so first you need to label so that I know you're finding the right theta. 18-foot ladder, that is 18 feet right here. The window is 12 foot off the ground, so that's this side right here. Maybe better with a different color. This side right here is 12 feet. Okay, now, what is the angle the ladder is making with the side of the house? So this angle right here is theta. We are assuming the house is vertical, so it's a right triangle. So what I have is the angle theta, the side adjacent to it that's touching the angle, and the hypotenuse. Since we have an adjacent side, we have to use a cosine function. So cosine theta equals 12/18, which means that theta is inverse cosine of 12/18. And then put it into a calculator. This should be 48.2 degrees. Okay. Fundamental identities, to fully simplify the expression, you do need to show all the work. We are going to be, let me remind you of some really fundamental identities. So we have sine squared theta plus cosine squared theta equals 1. That's the Pythagorean identity. And then we have another form of the Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. Okay, on the first one, if you notice that this is this, then this becomes very easy. Look, cosine squared x times secant squared x. Now, cosine squared is still there, times secant is 1 over cosine. But I had secant squared, so this is 1 over cosine squared. And then cosine squared x on the top and cosine squared x on the bottom just reduce. So this is just 1. Okay. Now on the second one, I am going to use the fact that cotangent is odd to get this minus sign to the front, first and foremost. So this is cosecant x divided by negative cotangent x. Okay, then I'm going to change everything into sines and cosines. Don't drop the negative. So cosecant is 1 over sine. And then cotangent is cosine over sine. Don't forget the negative. Okay, fraction division rules. You leave the top fraction, the one that's in the numerator, you leave that alone. You change division sign to multiplication, and then you flip the fraction that was in the denominator, and it is negative for us, so don't lose the negative sign. Sine x over cosine x this time. You will reduce the sign on top and the sign on the bottom, leaving you with negative 1 over cosine or negative secant x. Eight is the same thing, just a little bit more intense problems here. We are using just the fundamental identities and, well, really just the fundamental identities looks like on these to rewrite these as a single trigonometric function. So on this first one, we do need to change everything to sines and cosines so that we can figure out what cancels out. Sine x times tangent is sine x over cosine x. Cotangent is cosine x over sine x. And then you have a couple of approaches. You can open up the parenthesis, so distribute the sine x and go from there. I found that it's a little bit easier to combine the fractions inside the parenthesis first and then go from there. So I'm going to keep the sine x on the outside for now. And then inside, the greatest common denominator is cosine x times sine x. So the first fraction I would have to multiply by sine x over sine x. So this is sine squared x. Plus, the second fraction I would have to multiply by cosine x over cosine x. So this is cosine squared x. And the common shared denominator is sine x times cosine x. Now, you do have to recall or recognize that this is the Pythagorean identity, and it's just 1. So this is sine x times 1 over sine x times cosine x. And then if you multiply this out, you're going to reduce the sine x on the top and the sine x on the bottom, leaving you with just 1 over cosine again, which is secant. I'll do part C first. On part C, we have sine squared x divided by 1 minus cosine x minus 1. Now I'm going to stop you right here. 1 minus cosine x is not sine x. We do have this identity, sine squared x plus cosine squared x equals 1. If you rearrange it for sine squared, you'll get sine squared x equals 1 minus cosine squared x. Now, this bottom part, the denominator, it does not have the cosine squared. So it's not, you cannot rewrite it as sine x because that's not true. What you can do is you can replace this sine x with 1 minus cosine x, which is what you should be doing here. So sine squared x will be replaced with 1 minus cosine squared x divided by 1 minus cosine x. Minus 1 is still there. Now, again, you cannot reduce the cosine squared on top and the cosine on the bottom. It doesn't work that way. Math would be a lot easier if it did, but it does not. You have to recognize that the numerator is the difference of two squares, and you have to factor it out according to the difference of two squares formula, leaving you with 1 minus cosine x times 1 plus cosine x divided by 1 minus cosine x minus 1. Now you can reduce 1 minus cosine x on top and 1 minus cosine x on the bottom, leaving you now with 1 plus cosine x minus x equals, and then 1 minus 1 is 0, so this is just cosine x. Cotangent theta plus tangent theta, and then divided by secant of negative theta. So first of all, secant is even, so you can just get rid of that negative sign. So cotangent theta plus tangent theta divided by secant theta, because secant is even. And then you just switch everything to sines and cosines to make sure that we know what cancels and what doesn't. On the top, cotangent is cosine over sine, plus tangent is sine over cosine, divided by, on the bottom, secant is 1 over cosine. Okay. On the top in the numerator, put the two fractions together. So again, they need the least common denominator, just like part A. They need the least common denominator of sine theta times cosine theta. So the first one, you're going to multiply by cosine theta over cosine theta. So this is cosine squared theta. Plus, the second fraction will be multiplied by sine over sine. So this is sine squared theta. They have a common denominator of sine theta times cosine theta. Then another denominator, there's still 1 over cosine theta on the bottom. Okay, on top, starting to blend in over here. This thing right here, that's just 1. So this is now 1 divided by sine theta times cosine theta, and then divided by 1 over cosine theta. Now fraction division, leave the top fraction unchanged, 1 over sine theta times cosine theta, replace division with multiplication, and flip the fraction that's on the bottom in the denominator. And you can cancel cosine on top and cosine on the bottom, leaving you with 1 over sine or cosecant. All right, and then part D, we have cosine x over 1 plus sine x plus tangent x. First of all, I'm going to rewrite tangent as sine over cosine. Let me do this. There we go. Okay. Cosine x divided by 1 plus sine x plus sine x times over cosine x. Now we're going to add these two fractions. The least common denominator is both denominators multiplied together. So when we are putting them, let me just do it step by step. Okay. Cosine x divided by 1 plus sine x. You're going to multiply that fraction by cosine x over cosine x to get the least common denominator. Plus sine x over cosine x. We're going to multiply this one by the other denominator over the other denominator. So here's what you're going to get. Cosine x times cosine x is cosine squared x divided by cosine x times 1 plus sine x plus sine x times 1 plus sine x divided by cosine x times 1 plus sine x. Now that they have the same denominator, I can just add the numerators, but before I do that, I'm actually going to go ahead and distribute this. So a couple of algebra steps all in one. So we have cosine squared x plus sine x times 1, that's just sine x, plus sine x times sine x is sine squared x, and then the one denominator, cosine x 1 plus sine x. Okay, I'm hoping that by this point you recognize that cosine squared x plus sine squared x is just 1. So this is 1 plus sine x divided by cosine x 1 plus sine x equals, notice that 1 plus sine of x on the top and 1 plus sine of x on the bottom do cancel. Be careful though, this is a 1, not a 0. So this is 1 over cosine x, which is secant x. Okay, verifying the identities. You do remember that you need to show me all the steps on this one. If I am questioning something, you will lose points. Let's go ahead and open up the parentheses, then figure out some trig identities, like terms, and see what happens. I am using shortcuts for the opening up of the parentheses. If you don't remember, this is a perfect square shortcut. So a minus b squared equals a squared minus 2ab plus b squared. Works with a plus sign also. I'm going to use both of them. Okay. So that's the first thing we're going to do is open up both of these parentheses. So the first one, this is going to be sine squared x minus 2 sine x cosine x plus cosine squared x plus the second parenthesis, sine squared x plus 2 sine x cosine x plus cosine squared. Oop, that's a funny square. Squared x. Then you need to realize that sine squared x and cosine squared x is 1. But we have two of those. Sine squared x and cosine squared x is also 1. So this is going to be 1 plus 1 minus 2 sine x cosine x plus 2 sine x cosine x. Well, it is fairly obvious now. This and this, when you add them as like terms, which they are like terms, that's 0, so that goes away, and 1 plus 1 is 2. So that is 2. We needed to get 2, we got 2. This shows that the identity was true. So that's the first one. I'll have 2 more here. On part B, it's actually super simple. You just have to recognize a couple of things. One of them is, again, the Pythagorean identity. It starts with the Pythagorean identity, but let's go ahead and rewrite it here. So sine squared x plus cosine squared x equals 1. And then if I solve it for sine, it would be 1 minus cosine squared x. Okay, on part B, on the left-hand side, if you factor out a cosine of x, then it's going to be 1 minus cosine squared x inside the parentheses. And then if you recognize that 1 minus cosine squared x is sine squared x, then it works right away. Very, very simple proof on this one. Now let's try cosecant squared minus cotangent squared, and it should give you a 1. And again, you could switch cosecant and cotangent into sines and cosines, do common denominators, put it all together. But if you remember that cotangent squared x plus 1 equals cosecant squared x, then immediately you can say, okay, well, that means that, well, actually, that's all we need here. Because if you replace this with this, you'll get cotangent squared x plus 1 minus cotangent squared x. And cotangent squared minus cotangent squared, that's 0, so this is just 1. Okay. Okay, sum and difference formulas to get the exact value for these trigonometric functions. So we'll go ahead and do that real quick. I'm going to use the fact that tangent is odd to go ahead and put that negative sign in front of the tangent sign on this time. So this is negative tangent of 105 degrees. Now we have to replace 105 degrees as a sum or a difference of two angles on the unit circle. If you can stay inside the first quadrant, it is recommended that you do so. So this will be minus tangent of 45 degrees plus 60 degrees. Okay, then according to the formula, this is negative, and then open it up according to the formula. So there's fractions in here, so write a little bit smaller. This is tangent of 45 degrees plus tangent of 60 degrees divided by 1 minus tangent of 45 degrees times tangent of 60 degrees. Okay, there's still that negative sign. Tangent of 45 is 1. Tangent of 60 is square root of 3 divided by 1. Ooh, no, it's not plus, that's minus. Minus tangent of 45 degrees is 1, and then it's multiplied by tangent of 60, which is the square root of 3. Now, this negative on the inside, on the outside, this negative right here, you should distribute it inside of the parenthesis, but you don't want to distribute it on top. Both values on the top are positive, so you don't want to make them negative if you can avoid that. So what you need to do here is distribute it to the bottom of the fraction where there is a negative sign. If you do that, the top will be unchanged, 1 plus the square root of 3 divided by, and then square root of 3 will become positive and 1 will become negative. And this will be your final answer. We'll go ahead and do part C this time. Cosine of 195 degrees. This is the same as cosine of 135 plus 60. Could not stay in the first quadrant this time. That's okay. Open it up according to the formula, some formula. So this is cosine of 135 degrees times cosine of 60 degrees minus sine of 135 degrees times sine of 60 degrees. Then from the unit circle, grab the values for those angles. Cosine of 135 degrees is negative square root of 2 over 2. Cosine of 60 degrees is 1/2. Minus sine of 135 degrees is square root of 2 over 2. And sine of 60 is square root of 3 over 2. So this would be negative square root of 2 over 4 minus square root of 6 over 4. And then put it together in one fraction. Negative square root of 2 minus square root of 6 divided by 4. Okay, part B would be in radians instead of degrees. So sine of 11 pi over 12. There's multiple possibilities. I'm just gonna go with the one that we didn't have in the notes. So we'll do sine of 11 pi over 12 is the same as sine of pi over 4 plus 2 pi over 3. And then open it up according to the sum formula for sines. So that is sine of pi over 4 times cosine of 2 pi over 3 plus cosine of pi over 4 sine of 2 pi over 3. Then from the unit circle, go ahead and grab the values. Square root of 2 over 2 for sine of pi over 4. Cosine of 2 pi over 3 is actually negative, negative 1/2. Plus cosine of pi over 4, square root of 2 over 2. Sine of 2 pi over 3 is positive square root of 3 over 2. So this is negative square root of 2 over 4 plus square root of 6 over 4. Putting it under one denominator, you can write it as negative square root of 2 plus square root of 6 over 4, but it is more common to put the square root of 6, the positive value, first. I'll accept both answers. You need to be comfortable with stuff like number 11, where you need to find the exact value of sine of alpha minus beta. If sine of alpha is negative 3 over 5, sine of beta is 1 over 5, and the terminal side of alpha is in quadrant 3, terminal side of beta is in quadrant 2. You do need to circle or box in your final answers. I need to be able to read your calculations, so especially if you are if you know you are not doing stuff in order, I have to be able to follow your logic. So please make sure that you are at least boxing in or circling your final answers, so I'm not hunting them down. You need to start by writing down the formula for sine of alpha minus beta. The formulas will be provided for you on the exam. Sine of alpha minus beta equals sine of alpha times cosine of beta minus cosine of alpha times sine of beta. I will go ahead and fill in what I know. Sine of alpha is negative 3 over 5, so negative 3 over 5 instead of sine of alpha, times cosine of beta is not given, but sine of beta is. So I still need, I'm going to mark them with a different color. I still need a number here. I still need a number here. But I do have a value for sine of beta, and it is just 1 over 5. I don't need parentheses, it's positive. Okay, now I need to calculate the rest of the values that I don't have. I'm going to go ahead and go left to right, so I'm going to find cosine beta first. equals. So we know that beta is in quadrant 2. So I am going to go ahead and draw a little triangle in quadrant 2. This is your angle beta. We also know that sine of beta is 1/5. That means that opposite side is 1 and hypotenuse is 5. What we need to find is that x, so the adjacent side to beta. X squared plus 1 squared equals 5 squared, Pythagorean theorem. So x squared equals 25 minus 1, so this is 24. X equals the square root of 24. Go ahead and take the partial. Square root of 24. 24 is 4 times 6, so this is 2 square roots of 6. Now, cosine beta, which is adjacent over the hypotenuse, would be 2 square roots of 6 divided by 5. Now, you do have to be careful with the quadrants. Since this is quadrant 2 and cosine is negative in quadrant 2, this is a negative value. Before I calculate the last thing that I need, I'm going to go ahead and fill this in where it's supposed to be so that I don't have to worry about it later. So this is negative 2 square roots of 6 over 5. Okay. And now I can go ahead and do the last thing that I need, which is cosine alpha. Okay, alpha is in quadrant 3. So I'm going to go ahead and write and draw a little triangle in quadrant 3. So this is alpha. We also know that sine of alpha is negative 3/5. So sine is opposite again. 3 over the hypotenuse. 5, we still need to find x. So x squared plus 3 squared equals 5 squared. X squared equals 25 minus 9, which is 16. X is the square root of 16, which is 4. Okay. Cosine alpha is adjacent side, which is 4, over the hypotenuse, which is 5. We're in quadrant 3, so we need a negative sign to go in front of that fraction. And I'll go ahead and fill it in right here. So negative 4/5. Now all you have to do is just algebraic calculations. The first two fractions are both negative, so the resulting value will be positive. You do multiply 3 times just the number outside of the square root, 3 times 2, which is 6. So this is going to be 6 square roots of 6 divided by 5 times 5 on the bottom, which is 25. The second two fractions, one is positive, one is negative, but I do have a negative sign in front of the negative fraction. So two negatives will make a positive. This is plus. 4 times 1 is just 4, and 5 times 5 is 25. Now put it together under one fraction. 6 square roots of 6 plus 4 divided by 25. And that is the final answer here. All right. Now we're doing the double angles. Still exact values. And this time you are given the value of cosine, and you need to find the exact value of sine of 2x and cosine of 2x. You cannot solve for x here. You have to use the double angle formulas. Okay, let's go ahead and start with the sine of 2x. Sine of 2x, the double angle formula is 2 sine x times cosine x. The double angle formulas are not on the formula sheet. You need to memorize them. So I already have the value for cosine x. What I don't have is the value for sine x, but I can find it. I know that the terminal side of x is in quadrant 4. So if I draw a little triangle in quadrant 4, This is my x. I know that cosine x is 1 over 5. Cosine is adjacent over the hypotenuse. I need to find the y value here. And what I'm looking for is sine x. So y squared plus 1 squared equals 5 squared. Y squared equals 24. Y equals the square root of 24, which is 2 square roots of 6. We already had that earlier. Sine of x is 2 square roots of 6, opposite side over the hypotenuse, which is 5. We are in quadrant 4 though, and sine is negative in quadrant 4. Don't forget to put a negative sign on it. And then now we can just plug it into the formula and do some calculations. So this is 2 times sine of x, which is negative 2 square root of 6 over 5, times cosine of x, which is positive 1 over 5. Multiply all the numbers on the top. If you need to, you can put a denominator of 1 on the 2. Straight across, 2 times negative 2, that is negative 4 times 1, that's negative 4 square root of 6 divided by 1 times 5 is 25. Okay. And now we also need cosine of 2x. That formula is cosine squared x minus sine squared x. We know all the values here now. So cosine was given to us, that's 1 over 5. We have to square it. Minus sine squared, that's negative 2 square root of 6 divided by 5, and we have to square that. Okay, order of operations, please don't distribute that negative sign. This is 1 over 25, square stuff first. On the inside of the second parenthesis, I know it's negative, but when we square it, it becomes positive. You square the 2, that's the 4. Square root of 6 is just 6, squared is just 6, and 5 squared is 25. So that's 1 minus 24 divided by 25. So it's negative 23 over 25. Okay, very, very similar problem here. Find the exact value of sine of 2x if cosine of, oh, not x, 2 theta, if cosine of theta is 3 over 5 and theta is between 270 degrees and 360 degrees, so in quadrant 4. Let's go ahead and mark that. This is quadrant 4. And once again, you cannot solve for theta, so write down the formula first. Sine of 2 theta equals 2 sine theta times cosine theta. We are given the value for cosine theta, but we are not given the value for sine theta. I know that theta is in quadrant 4, so again, a triangle in quadrant 4, x and y. I also know that cosine of theta is 3 over 5, so 3 is the adjacent side, 5 is the hypotenuse. We need to find the y. And we are looking for sine of theta here. So y squared plus 3 squared equals 5 squared. Y squared equals 25 minus 9, so 16. Y is the square root of 16, or 4. Sine is opposite, which is y, and it's just 4 over 5. You need a negative sign since we're in quadrant 4. And then plug in all the values. So this is, I guess I'll go back to green. This is 2 over 1 times sine of theta, which is negative 4 over 5, times cosine of theta, which is 3 over 5. Multiply the tops. 2 times negative 4 is negative 8, times 3 is negative 24. 1 times 5 is 25. A variation of this question, do pay attention to details here. Use the figure below to find the requested half and double angle values. On part A, we're just finding sine of 2 theta, so it's very similar to what we've just been doing. So sine of 2 theta equals 2 sine theta cosine theta. Let's go ahead and actually find the sine and cosine of theta. So theta is this angle right here. We don't know the hypotenuse, so that's the first thing we need to find. H squared equals 5 squared plus 12 squared. H squared equals 25 plus 144. H squared is 169, which means H equals the square root of 169 or 13. So that means that sine of theta is opposite, which is 5 over 13. And cosine of theta equals adjacent, which is 12 over the hypotenuse, which is 13. Okay, so when we're plugging them in, this is 2 times sine theta, which is 5 over 13, times cosine of theta, which is 12 over 13. 2 times 5 times 12 is 120, and 13 times 13 is 169. And that is the answer to that question. Nothing is reducible here. Now, little bit different. Do pay attention to the letters. Find cosine of 2 alpha this time, not theta, alpha. Angle alpha is right here. For alpha, sine alpha is opposite, which is 12 over the hypotenuse, which is 13. And cosine alpha is adjacent, which is 5 over the 13. Cosine, the double cosine formula is totally different from the double sine formula. Cosine of 2 alpha equals cosine squared alpha minus sine squared alpha. And then you're plugging in the values for alpha from above. Cosine is 5 over 13. You got to square that. Minus sine, which is 12 over the 13. You got to square that. Okay, so this is 25 over 169 minus 144 over 169. Subtract the values on the top, 25 minus 144, that is negative 119, and the common denominator is 169. Okay, the list of formulas in the unit circle is attached to this review. So the formulas that are on this list, that's the only formulas you're going to get on this quiz and on the subsequent exam too. So notice on the double angles, only the tangent is given. You need to know the sine of 2x and the cosine of 2x.